Hi everyone. So today what we're going to do is start to put together some of the things that we've been looking at over the last couple days. All the things we've been looking at, the moments, the free body diagrams, the breaking forces down and adding forces together, all are part of a topic that we're going to call statics. Now, statics is basically the study of forces and how they affect not just objects as a whole, but the individual parts of an object. For example, you see this is a scaffolding that holds up a set of lights. We're not going to look at just the object as a whole, but we're also going to look at each individual piece and say how much force is on this piece. Is it tension? Is it compression? And how much is it? We're going to do this primarily in bridge-shaped objects, but the idea is the same for whatever you want to use it for. Now, when we talk about statics, the key word here is static. Static meaning that it's a stationary object or that at least the object is not accelerating. So an object that's moving, as long as it's not speeding up or slowing down, we can also use statics to calculate the forces. All right. And the reason we can do this is because of Newton's first law. So Newton's first law tells us that an object in a state of rest will want to stay at rest, and an object in motion will want to continue in the same motion. And this all comes down to Newton's second law, which is that the force on an object equals the mass of an object times the acceleration of an object. So, since all objects have a finite mass, it's a number of some sort, what you can say is that whatever force you have causes an acceleration. So the only way to not have an acceleration, which is what we need for statics, no acceleration in statics, is that the force equals zero. Now, when we say force equals zero, we don't mean that there's no forces on it. We just mean that they're canceling out. So for example, if I have an object and I'm pushing it against the wall, and I'm pushing with 10 pounds of force on, let's say, a book. So I'm pushing a book against the wall with 10 pounds of force. I'm pushing with 10 pounds of force, but the wall is also pushing backwards on the book with 10 pounds of force. So those two 10-pound forces cancel out because they're in opposite directions. So what we mean by saying no force, so that there's no acceleration, is actually that there's no net force, which means when you add the forces together in a certain direction, that it equals zero. We can have lots of forces, it's just when we add them together on any particular direction, it needs to be zero. And what we also know is that for every action, there's a reaction. Now, we just demonstrated one of these topics. I was pushing the book against the wall, and the wall was pushing the book back. So that is a reaction. Now, we've already talked about this a little bit. We had talked about how some forces, particularly like pins and rollers, are reaction forces. They push back. In this case, the wall is providing a reaction force. If I'd push with 15 pounds of force, the wall would push back with 15 pounds of force. It's dependent upon how much force you're pushing on it with. Either way, we can only use statics when an object is in what's called static equilibrium. And this just is basically the same thing we've been talking about. What we mean is that there's no net forces on the object. Whether it's stationary or in constant motion, there's no net forces. So how do we do this? What we've been saying is no net forces in any particular direction. Now, up to this point, you guys have seen how we can take an X and Y force and combine them together to make another force, or we can take a force that's at some angle and break it into its X and Y forces. We're only going to be dealing with two-dimensional objects, so objects that have an X and a Y. We're not going to deal with a Z-axis. So we're going to take all of our forces and break them down into X and Y components, and then add all the X forces together and add all the Y forces together. And if all of our X forces equal zero and all of our Y forces equal zero, that means it's a static object. And everything we're going to be looking at is a static object. So these two laws are the first two laws of statics. Put these in your notes, underline them. They're key to doing what we're going to be doing for statics. So what we know is if we add up all of the forces in the x direction, it's going to be 0, and that's what this big E shape means, add up. So we're going to add up all of the forces in the x direction, they're going to be 0, and we're going to add up all of the forces in the y direction, and they're also going to be 0. So since we have no forces in either the x or the y, we know that we have no net forces whatsoever. Now, an object could be not moving in the x direction and not moving in the y direction, but could be rotating. Now, that obviously would be not a static object. So we also have to say that the sum of the moments is 0. And we've actually used this equation before when we were looking at moments and using them to calculate some of the forces. So this is our third and final rule of statics, is that when we take all of the moments around any point, and remember a moment is a force times a distance, whenever we take the moments and add them all up, the moments are going to equal 0. So just a couple quick things that we've looked at. Remember we talked about scalar and vector quantities. A scalar quantity tells you how much there is, but not what direction it's going. So for example, I could say I'm going 80 miles an hour, or I could say, it's 50 degrees outside, but they don't really tell you any direction. Now degrees, that wouldn't make sense, but if I wanted to use vector quantities, not only do I need an amount, a magnitude, but I need to say direction. So instead of just saying I'm going 50 miles an hour, I could say I'm going 50 miles an hour east. And this comes in important because you remember we're taking forces in certain directions, which is key. Remember we have a sense, this one is up and to the right, and we can break them down into their constituent parts, their x and y parts. We've used these all year, but the British system, which we're going to use mostly, we're using pounds force as our unit of force, and the metric system is going to be, of course, newtons. And you can convert between them using these conversions here. All right, and like we said before, we can have forces on the object, it's just they have to be counteracted. So for example, if I have a downward force on an object, for it to be in static equilibrium, I have to have an equal upward force. Or if I have a leftward force on an object, I have to have an equal rightward force. And not only do forces have to be canceled out, but we also have to do this with moments. So for example, if I have a clockwise moment, I have to have an equal counterclockwise moment for the object to stay in static equilibrium. And just if you're wondering, like, hey, how do I know if an object's in static equilibrium? The easiest giveaway is if it's sitting there and not moving, it's in static equilibrium. So all of the bridges and towers and every building, hopefully, that you see on a day-to-day basis is already in static equilibrium. And you'll remember a big part of this, since we need to find our forces in the x and y direction, like we did before, is taking a force that's at an angle and breaking it down into its x and y parts. And just as a quick last note, when we talk about static equilibrium and adding forces together, make sure you pay attention to the signs. We say that up is positive and down is negative. We say right is positive and left is negative. So this blue object, we have a 5-pound force and a 2-pound force. Since they're both going to the right, we'd say they're both positive. So positive 5 plus positive 2 equals positive 7. So it results in a 7-pound force to the right. With the red square, we have a 5-pound force to the right and a 2-pound force to the left. So the 5-pound force to the right would be positive. The 2-pound force to the left would be negative. So we'd have positive 5 and negative 2. So we ended up with a positive 3. So the force here is going to be positive 3, which means it's going to the right, 3 pounds. And notice, even though we have the same numbers here, the directions are important because we'll get 7 pounds on one and 3 pounds on the other. So we're going to explore statics more here as the unit goes on. Hope you all are being safe out there, and I'll see you tomorrow.